Hi, I'm David Koenig, a general practitioner in Exeter, and what I'd like to do in the slideshow is just share with you some insights from complexity theory and how they might be applied to certain areas of practice. And what I want to do is describe a shift in the way we see the world from this machine model, which has served us extremely well since the time of Newton. We understand systems by breaking them down into their component parts. But the model shifts to a complex interaction of a large number of elements that are shifting with time. You can't understand the system by breaking it down into its component parts, but patterns emerge from this local interaction. Complexus, from the Greek, braided together. And this is what I want to talk about. You could ask yourself, what on earth is a GP doing talking about complexity and systems theory? Well, in fact, my first degree was in chemical engineering, and I was a founder member of the Complexity and Primary Care group in the 90s. And at the time, we were an extremely hot group, but our fall from grace was almost as rapid as our acceleration to the dizzy heights. And I'll say a little bit more about why that might be in the conclusion. And I've in fact subtitled my talk A View from the Street. I did a book in 2004 entitled Complexity in Healthcare Organisation, A View from the Street. And I'd like to offer the perspective from the swampy lowlands of the coalface rather than the academic sunny uplands. Because behind every concept, behind every idea is a massive literature, most of which is contested, and in all cases is virtually inaccessible to those who actually get on and do the work. So I want to take this in terms of breadth rather than depth. I am in fact a generalist. In fact, my main interest now is in headache and migraine. I run the Exeter Headache Clinic for the NHS, and if anyone's got any problems, please do visit our site. Just Google Exeter Headache Clinic. Lots of useful information there, but that's beside the point of our main thrust here. So this is what I want to talk about. I want to start off with some general principles and some principles of general systems theory, which I think is a really important strand of thinking, of which complexity theory is one part. Then I want to say something about the basic principles of complexity theory, some of the challenges it has. Then I want to just briefly highlight some of the different perspectives on complexity thinking. One of the problems is that these ways of thinking have converged from a rather disparate array of disciplines, so you get different strands of thinking. I want to focus on two areas which I think are important. First of all, chaos theory, and the other area is self-organized criticality, which I think is quite an interesting concept. Then I want to move on into some practical applications. I think applying complexity to thinking about organizations is probably the most relevant for us working in the NHS, how we make decisions in organizations. I think there's some interesting thinking about how we might view health. Then I want to say a little bit about planetary and global health. I mean, the reason I'm putting this series of slides together is recently I did a special study unit for the medical school in Exeter on global and planetary health with a colleague. And there was a lot of talk around planetary health about systems thinking and complexity theory, but there was very little explanation of what this actually meant and what the implications were for that. So that was in fact the basis of this series of slides, just to give people a little bit more of a broader perspective of what complexity actually means. Then I want to go off piste a little and think a little bit about how complexity can map onto how we all began. And then finally applying it to language, which I think is a really important issue, getting slightly more philosophical, but I think it's really important. And then just a brief conclusion, and quite a lot of stuff I've put then into the appendix, as it really just clogs up the main flow of my narrative. I'm afraid on retrospect this talk is a little long, so I've put in this approximate timing slide. So I do drone on a little, I'm afraid, for which I apologise. So if you just want to flick back and forth, these are some timings you may find useful. So let's start by thinking how we make sense of the world. It's a bit of a frightening, crazy place out there, and we need to make sense of the world and act. And we do so by taking in sensory information and we codify this information in neural networks. And this information we put together in descriptive bundles, and we make causal inferences between these descriptive bundles. And this gives us our models of the world. The information that we take in, we store as models, and the vast majority of these models are implicit models. These models operate below the level of consciousness, and it's becoming clear that there's this area called the default mode network in the brain where the majority of these models are actually organized. And these models are what's called feed-forward models. They operate in difference. They anticipate what's going to happen, then they compare it with actually what does happen, and then the model is readjusted accordingly. So most of what goes on with these models ticks away at below the level of consciousness, but occasionally we actually can articulate explicit models which rise above the level of consciousness, and we can actually share these with other people and actually make them more specific by writing them down and sharing them that way. And there are a number of models on how we might approach the world out there, and I think wisdom is knowing which model is appropriate for the task in hand. Because I think it's important to realize that our symbols and representations, language, mathematics very much influence the way we collect and analyze data. And we must not lose sight of the fact that we impose our models on nature. They're only approximations. Nature is never just like that. Although probably mathematicians would say actually maths is actually how the world works. I'm not sure that's right. I don't think nature knows much about probabilistic statistics at a quantum level. I think we're always imposing our models on nature. And I think it was Maslow that says, to a man with a hammer, everything in the world is a nail. So that's a little bit about models. Let's think about general systems theory. Well, in fact, systems theory offers a systematic approach to explicit model making. I think that's a good starting point for understanding what it is. And it studies how observer-dependent elements interact to produce outcomes, and it derives general principles that we may apply more broadly across different types of systems. So first of all, we identify a boundary across which information or energy flows. And we look at the effect of modulating boundary filters, what comes in, what comes out. We look at what happens if you change the interactions and the feedback loops within this system. And we look at what happens if we change these processing algorithms, these transfer functions, that happens as one element takes in information and gives out information to other elements. And of course, the history of systems thinking goes back many thousands of years. This is a system from Hindu philosophy. I think it's quite interesting, yogic philosophy. And they were thinking about how these interrelated bits fit in to provide outcomes. So actually, systems thinking itself goes back many thousands of years. But it was only towards the end of the Second World War that systems thinking was really established as a formal discipline. And this was very much driven by the need to integrate these various weapon systems, particularly with the new evolving radar and other electronic devices. And systems thinking really got going in the 40s and 50s. And here are some of the key texts. I'm going to just flag up Ashby as a bit of a hero of mine. And Shannon, that single one paper in 1948 virtually underpins all of our information technology, all of our information transfer and communications this day. And these were all really important insights which we're using very broadly across a wide range of areas today. So here's Ross Ashby. He was the founding father of British systems thinking, and what I think is really interesting about him, because systems thinkers are part philosophers, part mathematicians, he was actually a psychiatrist. And actually how he got into systems thinking, I've really no idea, but he was very much influential in the early days. And of note, this was a really important law that he derived. And I've expanded that a little bit more in the appendix, and we will come across it as we go through this slide set. It was his law of requisite variety, which I think is a great name. And he said that if one system is controlling another, then the controlling system must have at least the same number of variables as the system it seeks to control. And I think this is really important, not just for control systems, but for systems when they adapt to each other. And we can in fact map this onto complexity thinking. And what's really interesting, you can see all his handwritten journals. Here's his widow with the 25 copies of his handwritten journals. And you can just imagine she was probably about to sling them out in a skip, and someone said, well, hang on a second, those might be quite interesting. And they're in fact now in the British Library, and they've all been digitalized, and you can access them online. And dipping into them will give you a really interesting insight into the mind of a systems thinker. So how do we draw up systems thinking? What's the best taxonomy for looking at all these various types of systems? Well, I think the best way is, and the simplest way, is to look at a simple diagram depending and place these various strands of systems thinking as to whether systems are hard or soft. That is, they can be described mathematically, or mathematical description is problematic, and the best we can obtain is qualitative insights. And whether they are linear or seen as non-linear. Linear systems can be understood by breaking them down into their component parts, whereas non-linear systems cannot be done so. And just to give you an example of what's actually out there, this is just a map of the complexity sciences alone. So systems thinking is a massive field of which there are many strands. I'm not going to go into this in any detail, but you can see even just within the complexity sciences, there are many strands of thinking which will map onto this picture. So of interest to us are chaotic systems, which we'll briefly allude to. These are hard nonlinear systems, but of more interest to us is the softer area of the spectrum, complex systems and complex adaptive systems. So let's just look at the difference between a linear system and a nonlinear system. I think this is a really important differential to understand if you need to understand a bit about complexity theory. So in a linear system, we get this concept of additivity that applies. So you can understand a linear system by breaking it down into its component parts. So the function of the overall system is the addition of the function of individual elements. And with a linear system, information flows continuously, feedback is negative, and the focus here is on maintaining a constant output. And the metaphor is the system as a machine. So you can understand it by breaking it down into its component parts. And a part in one machine will have exactly the same action in another machine. Someone can sit outside the machine and design it and engineer it according to its desired outcome. It's linear. If you press the accelerator, it will go faster. If you press the accelerator more, it will go faster again. It's predictable or deterministic. If you know where you are at t = 0, you know where you can be at any time in the future. And I particularly like the chap in the back. If you don't understand what's going on, all you need to do is increase the level of analytical sophistication and you can understand what's going on. The truth actually is out there. The truth will yield, providing you throw enough analytical detail at it. And this is the model that's served us well since the time of Newton. This is the model where modern science sits. It's predictable, it's reductionist. You can understand the system by breaking it down into its component parts. It's complicated but not complex. We're going to be looking at complex nonlinear systems, and this principle of additivity does not apply. So the overall function of the system, how it operates, does not equal the sum of the parts. And I just want to go through now some important complexity principles that really underpin how we might think about systems that we see as complex. So system elements process information, they take in information, there's an algorithm or a transfer function, and they give out outputs accordingly. This transfer function can remain stable, so we call these systems complex systems, or if this transfer function changes with time, for example, as we learn or as the algorithm is changed, we call these complex adaptive systems. And these elements act predominantly on the local information they're presented with. In some cases you can get information from more distal areas, but information is predominantly local. And we call this interaction, this transfer function, simple or local rules. So there are a large number of elements, they're dynamic, they change with time, there's no fixed outcome. These systems can operate away from equilibrium. So for example, living systems operate away from thermodynamic equilibrium. Their temperature is not the same as their surrounds. And they have these characteristics of non-linearity. Information is modulated across each element, and this transmission is reiterative. The output of one transfer function feeds back into another element in a recursive or reiterative fashion. And it is this recursive interaction that leads to their nonlinear characteristics. And nonlinear characteristics are such that small inputs in one part of the system can have a very large effect elsewhere, and vice versa. And we can see this as the butterfly effect. A small input in the system in one part, say here, can stretch and fold as it gets modulated across the system, and there can be a very large output here. So the butterfly can flap its wings in Tokyo, and there can be a hurricane in Florida. And these systems, unlike our machine model, cannot be understood by breaking them down into their component parts. Within these systems, there are both positive and negative feedback loops, and this leads to what we call emergent patterns. These systems can self-organize to reflect the constraints on the environment, and patterns emerge which could not be predicted on the analysis of individual elements or units. So here's an example of self-organization, stable patterning emerging due to local interaction. There's no complex algorithm or computer program inside this acorn that decides it's going to be an oak tree. There's probably a simple number or we can apply a model of a simple number of recursive rules from which a pattern will emerge. This concept of self-emergence, simple rules, is quite usefully applied to shoaling or flocking of birds. So how do these fish operate in these shoals, or how do birds flock? And you can model this behavior very well with the recursive application of three very simple rules. So it's the interaction at a local level underpinned by guiding principles or simple rules from which complex behavior can emerge. The other insight in complex systems is the history of the system is really important. It's really important to where you've come from. This determines very much where you are at the present time. And system boundaries can be problematic. The boundary in complex systems is very much observer dependent, and sometimes may often reflect the prejudices of the observer rather than any factors of the process itself. So we need to be very cautious about boundaries. The butterfly is always flapping its wings, and he may be very well away from the system we're looking at under consideration. So those are some of the main implications of a shift to a complexity frame of reference. We need to be cautious over breaking systems down to understand them. Small inputs in one part of the system can have very large effects elsewhere, and vice versa, so we need to be very aware of unintended consequences. Systems can self-organize due to these recursive, positive and negative feedback loops within them. And system patterns evolve from local rules applied in real time, not top-down global principles. So there is limited opportunity to stand outside the system and engineer it to where we want it to go. We need to be cautious about where we set our boundaries, and we need to be mindful that system history is important. So those are some of the fundamental starting points of a complexity frame of reference. And as I alluded to, we can apply Ashby's law to complex systems, and this important concept of complexity matching. Complex systems can in fact synchronize. This has regulatory and adaptive advantages, and it represents a strand of Ashby's law, and we'll come back to that again when we look at applications of complexity thinking. And there's also a danger of gluing together partial studies of complex systems. I've alluded to previously that boundaries are very problematic, and it has been suggested you need to study the whole system rather than the individual bits to get some sort of idea of what's going on. So our model, or our metaphor, in fact, shifts from the linear modern science approach of a machine to an ecosystem of co-evolving elements. So complex, complicated, complex. And if you take nothing away from this talk, perhaps you will not conflate complicated and complex as many people do. I think it's quite interesting to map these approaches onto other areas. So I think it maps very much onto our Western approach. What does it consist of? Whereas a nonlinear approach you can map onto an Eastern philosophical approach. How is it patterned? So they're much more interested in pattern, whereas we're much more interested in substance. We die to dissect. You can map it onto left brain. The linear system approach maps very much onto this left brain, right brain. It is said that our right brain is far more sensitized to non-linear patterns. And I know it's a bit of a controversial area, but I think it's useful even as a metaphor. So that is some of the general principles of complexity theory, which we're going to move on to apply. But before I do that, I just want to highlight briefly some of the limitations and challenges of this way of thinking. So our first problem is it's very difficult to quantify complexity. We die to put numbers on things. We love to quantify things. And it's very difficult to do that with complex systems. There have been a large number of attempts at various things at different degrees of simplicity or complexity, but there's been no useful way of doing that. So for example, if we look at algorithmic information complexity, this is the minimum number of lines of computer code that will describe a complex system. So a number of ways, but nothing really satisfactory. These systems are also not only difficult to quantify, complexity is difficult to quantify, but they're very difficult to model mathematically, particularly relating micro behavior to macro behavior. So there are no mathematical principles relating what goes on at a local level to these patterns that emerge on a macro level. And there are particularly major challenges modeling humans, the transfer functions. I mean, humans are complex adaptive systems, and our transfer functions change rapidly depending on the context. So we use abstraction and metaphor, and what we say is often not what we think, and what we think is not what we say or what we do. So challenges exist for modeling humans, and in fact it has been said that the only valid model of a human system is the system itself. So we have to be very cautious if we start applying these insights into human systems, as we quite often do. And finally, there are problems with terminology and metaphor transfer. As I alluded to earlier, these insights are converging from a whole disparate range of disciplines, and there's different terminologies, different metaphors, and we need to be cautious about inappropriate metaphorical transfer. So still a number of challenges. Complexity thinking certainly offers us qualitative insights, but as yet not the quantitative insights that Western science has been predicated upon. So in the next section, I want to just highlight some of these strands of complexity thinking that have been converging that I have alluded to previously. And this is what I want to pick up on. And let's start with self-organized criticality. So we can look at systems, three types of general systems. There are systems that are interacting with low connectivity, patterns are stable, and these patterns consolidate over time. So they're not exploring their possibility state. The system is not changing very rapidly. These are relatively low energy states. Then there are these very high energy states where the systems are unstable, they're highly connective. These connections are breaking down and reforming all the time. They're highly innovative, but these gains are not consolidated. And somewhere in the middle, there's this optimum position where systems are maximally adaptive, and each element is optimally fit without disrupting the fitness of the others. I think that's a useful starting point to think about this area. And we call this area self-organized criticality. And in many cases, this is where complex systems will self-organize too. So systems need to be effective, they need to be efficient, they need to be innovative, and they need to be resilient. And these are, in a way, mutually exclusive, some of these terms. So what's efficient is not usually resilient, what's efficient is not usually innovative. What is innovative usually doesn't minimize energy expenditure, and energy expenditure is in fact the primary motive of all, certainly living systems and most design systems. But complex systems are able to optimize to their environmental constraints. And they self-organize to this position. And what's interesting is when they do this, they demonstrate power law scaling. And I think this is probably the most appropriate mathematical way of thinking of, or certainly the most accessible way of thinking of complex systems when they're at this state, which is can be not in all complex systems, but when systems are at their maximum state of adaptiveness. And in this state, the log of the size of the event is proportional to the log of the frequency with which that event happens. This slide shows the difference between a normal distribution with which we are familiar and a power law distribution, which shows a large number of small events and a much smaller number of large events. And if you plot those two axes on a log scale, you'll have a straight line. So let's just look at some examples of this. And for some reason, sand piles is one that sort of is a recurring theme. So this distribution can occur both in natural and living systems. So if we just pile sand up at a constant rate, it will reach a critical slope where it will go no further, but it won't all collapse at once. There'll be a whole range of avalanches with time. Some will be small, some will be large. And if you plot this on a log graph of frequency of avalanches against avalanche size, you'll see that it is a straight line. So this system has organized itself to a position of self-organized criticality. But you can see this in natural systems. Here's forest fires. Size of a forest fire against the frequency with which it happens. Again, log is a straight line. This is earthquake, size of earthquake against frequency of earthquake. This is a human system. This is messages on Twitter, size and frequency. It has been demonstrated for waiting lists in the National Health Service. This is a physiological example. These are different people with the log of their beat-to-beat time against the frequency of that time. And again, you can see power law distributions are in operation, inferring that these are complex systems that have adapted themselves to this position of self-organized criticality, where the system is maximally fit and maximally adaptive to its environmental constraints and changes in its environment. So what about the brain? Well, in fact, the brain does show all three types of dynamic behavior. Certainly there are areas of very high interaction, almost random. Then there are areas of very regular interaction. But we can also demonstrate areas where there is self-organized criticality. Scale-free is another name for self-organized criticality, because these systems show same dynamics at different levels of scale. So the brain has a combination of these three types of dynamic activity. And here you can see a part of the brain that's operating in an area of self-organized criticality, power of the brain signals against the frequency at which that power is found. You can see there a straight line operating here. So what we can say is that separate areas can organize independently, and the evidence suggests that high levels of input will cause criticality to decrease. The internal dynamics tends to be replaced by external triggered activity if it's at a significant level. But what's really interesting is that self-organized criticality decreases after prolonged wakefulness and in fact increases after sleep. Now we don't know what sleep is all about, but could it be a function to restore the brain to a state of self-organized criticality, which is an interesting proposition. So self-organized criticality and power laws do offer us an enticing approach to analysing, a top-down approach to analysing complex systems. And it is enticing because we don't have an analytical bottom-up approach. But we do need to proceed with caution. It's a contested area, and there are other ways that systems can demonstrate power laws other than complex dynamics. We need to make sure we're not carried away by its simplicity, but on the other hand, the principle of Occam's razor tells us that often the simplest theories are the best. So this approach of self-organized criticality and power laws may be useful for us when we talk about complexity matching. And it may be that maximum synchronicity occurs when systems are not only at criticality, but share their power law index. But this is an area in which we need to proceed with a considerable degree of caution. So let's look at some of the other threads of thinking. Very briefly, we get from fractal geometry, Mandelbrot, this is the fractal scaling, these pictures, beautiful pictures that have self-similarity at different levels of scale, and you can keep on amplifying and looking at deeper and deeper and deeper levels of scale, and they still show similar self-similarity at different levels. Fractal scaling. Fractal scaling is a feature of many complex systems. At whatever level you look at them, they show self-similarity at different levels of scale. So nature is in fact based on fractal patterns. This is the bronchial tree. This is spatially fractal, self-similarity at different levels of magnification. The second thread that's come really from chemistry and physics, the work of Prigionine, is this concept of dissipative structures. And I think a really interesting observation is that, and I'm going to pick this up again in the appendix, where we ask ourselves where complexity comes from. As the entropy of a system increases, then the complexity of this system rises to a certain point before decreasing and going back to randomness. And this is a really important insight, which we will pick up again when we come to looking at the evolution of life forms, because entropy, the second law of thermodynamics, is continuing to increase in the universe, but there is a small opportunity of time where complexity is maximized. And this was Prigionine's starting point, and this happens in systems that operate away from equilibrium, thermodynamic equilibrium, to which energy is applied. So as you apply, this is water, and as you apply heat, energy into this system, the entropy of the system gradually increases until it boils. But on that way to boiling, the complexity will increase until at a maximum you get this mechanical patterning where the hot water is rising and the colder water is dropping. You get these circulatory currents, or Bernard cells as they're called. So for a brief moment, complexity is maximized before it then breaks down and the whole thing goes off to boiling point. And this is an example of dissipative structures. Structures that operate away from equilibrium can self-organize at a critical point. These are dissipative structures. Autopoiesis is another thread of thinking, which is important when we come to look at how life may have formed. And this suggests that bounded systems can form, and these bounded systems form networks of processes or reactions, which in turn form components, which then in turn feed back on the boundary system itself. And this boundary system forms new networks of processes, and you get this autopoietic, or this self-referential enclosed system, which changes over time and can adapt as this bounded system takes in information from other systems around it in a process called structured coupling. Cellular automaton is a computer science approach, and this is basically the computer science approach to nonlinear simulations. And I think this can give us some useful insights when it comes to thinking about simple rules. And I think a good example here is how the application of simple rules locally from that the self-organization can arise to more complex patterns. And this is a good example here is the computer simulation called the game of life, when squares are highlighted at random, and there are, I think, 5 simple rules that operate at a lower level. I can't remember what they are, but it's something like if there's a square next to you, you reproduce. If there's 2 next to you, you die. Or then there's 5 rules, very much simple rules like that. And you can start the whole thing. So if we play out these simple rules, depending on where our starting conditions are, you can see how this recursive interaction of a very small number of simple rules can give rise to emergent patterns that are quite complex. And in fact, you can see how just one slight variation in your starting point or a mutation could give rise to a very different pattern. Very different pattern could emerge, to which we can apply Darwinian principles of natural selection. So we can map that on to, and I will do in a few slides time, how life may have formed. Self-organized criticality from the recursive application of simple rules. The other main strand of thinking has come from mathematics. This is chaos theory, and I'm going to focus in a little bit more detail on this because I think it's a contested area, the relationship between chaos theory and complexity theory, but I think it's quite useful. I find it quite useful for looking at insights on how chaos theory can apply to complexity theory and underpin some of the principles of complexity theory. So chaos theory is a particular type of behavior that occurs in nonlinear systems, albeit with a limited number of variables. And what really defines these systems is their exquisite sensitivity to initial conditions. And Pontcaré was a French mathematician who was really sort of flagging up at the turn of the 1900s that things weren't quite as sure as they seemed to be in Newtonian mechanics. And he was focusing on this 3-body problem. In Newtonian mechanics, you can calculate the trajectory of eclipse fairly straightforwardly, but when there's 3 interacting eclipses, 3 interacting bodies, Newtonian mechanics seems to break down, and he couldn't establish an answer to this. So there was something else that was going on. There was some other model that was needed for this slightly more complex behavior. And the story gets picked up next in the early 60s by Lorentz, who was a meteorological physicist. And he had a simple computer model for the atmosphere, behavior of the atmosphere. And I think something went wrong with it halfway through, and he went away for lunch, and he came back and decided rather than go back to the start and start all over again, he'd pick it up from where he left off, and he re-inputted the variables. But one of the variables, I think he changed a decimal point by 0.1 or a very small amount, expecting that it wouldn't make any difference. But what he actually noted was there was a massive divergence in how this system evolved in his program. So this was a recursive program. So he came across this phenomena that there are certain types of systems where a very small difference to input or system characteristics can lead to a very marked difference in output. This is the butterfly effect. And I think this is a useful starting point to understand what's going on with nonlinearity. And we'll just go through this very briefly. So we're looking here at a model of fish swimming around in a pond, and as they reproduce year after year, they reproduce once a year, so it's reiterative, it's recursive every year. As the number of the fish in the pond get larger, the food supply goes down, so the fish go up next year. So there's this recursive operation as the system is stretched and folded. So our basic equation is the number of fish next year equals the birth rate times the number of fish this year times the number of maximum number of fish in the pond that can occur, subtract the number of fish that occur this year. So that's our basic starting point for a nonlinear equation. So let's look at numbers of fish year on year. So with the birth rate fairly low, we have this repetitive cycle of pattern. But as we push up the birth rate, the number of fish in the pond seem to break down and seem to go into some sort of irregular pattern. If you plot this out, normalizing the maximum number of fish in the pond to 1, we can see that as the birth rate increases, we get this increase in regular numbers each year. And then all of a sudden this pattern breaks down. But the system is not random, there is an underlying pattern to it. So this is very exquisite to initial conditions, and just a very small change in the birth rate can lead to very drastic changes in underlying pattern. And if we look at this at different levels of scale, we can see self-similarity at different levels of scale. We can blow this up and look into a very fine, very small area, and we'll see similar patterns. So this is behavior that looks random, but in fact has an underlying pattern and is in fact deterministic. The problem is with being deterministic is we have to know exactly what starting conditions are. We can never know what the exact starting conditions are because of this extreme sensitivity. This is very difficult. So although in theory these are deterministic systems, in practice they are not. And I think one of the big problems here is this conflation of the word chaos. Chaos is not randomness. And I think this is a big disservice to the whole community from then onwards. We often conflate chaos, as we're seeing here, non-linearity behavior, which is exquisitely sensitive to initial conditions, with chaos as in randomness. The two are very different. I just want to push this on into 3 dimensions, and I think this is the basis of Lorentz's model. We needn't worry too much about it, but it's just how the atmosphere, a particle in the atmosphere in convection currents, was projected between 2 temperatures, T2 and T1, within a 3-dimensional space. Here's the reiterative equations that he was using. The output of one equation feeds into the input of the next. And we follow this trajectory, and we can see that the trajectory is not everywhere in space. It is on what we call an attractor on a specific area of this 3-dimensional space. And this concept of attractors is quite important in chaos theory, and I think metaphorically important. I find it quite useful in complexity theory as well. And these are areas of space that all trajectories tend to occupy, but they are still exquisitely sensitive to initial conditions. So if you started here, there would be a trajectory keeping on this attractor. If you started minutely close to it, it would start off similarly, but it would diverge very quickly. So those are attractors in phase space. And there are various measures of chaos. We've looked at power law scaling if they demonstrate that behavior. But dimensionality of the attractor is another way of measuring chaos. So I won't say anything more about chaos, but I think it's quite useful to map those principles onto how we think about complex systems. So let's get on to some of the practical applications of complexity thinking. So organisations, how we understand them, how do we make decisions in them? The NHS is, well, it's probably more like a random system than a chaotic system. Chaotic in the lay sense of the word. And if you want to know how the NHS works, this is a really good, just Google King's Fund how the NHS works. This is a really good cartoon demonstration of how the NHS works. But what I want to do is, as a starting point, follow the work of Snowden, which I think is quite useful. And his Cynefin, he was a Welsh guy, and so I think this is where he lived in North Wales. This is his framework. And he sees organisations or systems, any systems in fact, as in terms of simple, complicated, complex or chaotic. And depending on which system you are in, and of course you need to have a good idea and there needs to be agreement between all stakeholders about what sort of system you're in, will determine how you actually act on or in that system. There's a huge literature out there on how organisations do and don't work, but I think this is a useful starting point from the perspective of complexity theory. So let's look at the simple zone. This is a linear zone, simple relationship between cause and effects. Here, we know everything about the system. Facts are clear. We have all the information at our fingertips. The answers are self-evident. There's no, it's not contested how the evidence that's around. Everyone is in agreement with it. And in these systems, they sit within a bureaucratic framework of rules and regulations. We can delegate. There are dangers of complacency, and best practice does change, but in general, things are fairly straightforward. So this is the zone of known knowns. We know everything. We sense, we categorize to where we are, and then we can respond appropriately within our bureaucratic frameworks. And this is the area of best practice frameworks. The next type of system we may find ourselves in is a complicated system. So this is still linear, contains a number of different more simple systems all integrated together. So there may be multiple correct answers here, not one correct answer. And this is the domain of experts. And here the analysis requires expert opinion and expertise. There may be best practice going on, but it's not always easy to access. And the downside here is that if you're following experts, experts tend to operate in silos, and the danger may be in trained thinking amongst experts. And here we know what we don't know, and the mode is sense the system, analyze it, and respond accordingly. Good practice frameworks predominate. This is the zone in which our focus of attention is complex zones. Here there is unpredictable responses. The system is non-linear. The setting of boundaries, as we've seen, is problematic. We can hopefully establish local rules, and there has been quite a drive to look at organisations by understanding what the simple rules are and change them if you can. There are lots of pros and cons about that, but I won't go into. But in general, the focus is on encouraging rich interaction at a local level, because what the system becomes emerges from interaction at a local level. So we encourage diversity and experimentation. We set up an architecture within our organisations for discovery, not performance. And as we do this, we identify emerging patterns, and we amplify those positive ones, and we try and dampen down the negative patterns that are emerging. Being prepared to fail. And the danger in these systems is thinking we can stand outside the system and impose order upon them, and not adequately identifying patterns as they're emerging. So here we have unknown unknowns. There's stuff going on that we don't know that we know about. And our modus operandi is to probe, sense, and respond. We have to get in the system, do some small perturbation to the system, see what happens, and make an appropriate change. And this is where complexity insights come from. This is where our practice changes to emergent practice, recognizing emergent patterns. There is a fourth zone, which known causes calls chaotic. Here again, this is a misnomer. It's not anything to do with chaos. I think it should be random, actually. Here's a disordered system where there's no cause effect possible at all. And here we have to do something quick. So we have to act quickly to establish order, to get it back to probably a complex system or even a complicated system. So we sense and entrain stability, and the danger here is not being forceful enough, in fact. So there's no cause effect in the system at all. We act, we sense, and then we respond accordingly. And this is the zone of stabilization, crisis management. Hopefully that doesn't occur too often. I think that's quite a useful structure to start organizing our thinking about organizations that we may find ourselves in, matching the task to the context of the system in which we find ourselves. I applied this to the consultation in general practice, and I think there's another zone that comes in here actually, and I put in a transitional zone between complicated and complex. So, for example, this is an influence diagram for this transitional domain. In a transitional domain, we know what the variables are. We know the direction in which the variables will shift the system, but we don't know to what extent. So, for example, if you exercise, you know that it's going to improve obesity, and it will improve your vascular disease. And if you improve your obesity, you'll improve your hypertension. So we know how the system is going to be moving, but we don't know it in any quantitative detail. So I think there is a transitional domain in this spectrum that we need to be aware of. So that's very briefly about complexity thinking applied to organisation. It's a massive field and there's huge amounts of stuff there, but I think David Snowden is a good place to start looking if you want to look on YouTube. But I want to move on now to apply complexity thinking to thinking about health. So what is health? Well, prior to 1948 and the inception of the National Health Service, quite straightforward. Health was just lack of disease. But in 1948, the World Health Organization started expanding this concept. And not only did they look at physical well-being, that they also said that health was a state of social and mental well-being. And this was a big and very significant shift. But the perspective was still very much within a linear framework. Homeostasis was the signature of health. A fixed outcome, whatever, irrespective of what that is, was the signature of health. In 1984, things shifted again. The World Health Organization added to physical, social and mental well-being health as a resource for living and satisfying needs and ability to flourish. Now we need to unpack what that actually means. So the perspective of health from a non-linear perspective sees hemodynamics. We'll start by seeing looking at the hemodynamics as a signature of health rather than an artificial static. And our starting point would be to look at systems as a dynamic interplay between multiple regulatory mechanisms. And it is this interplay that preserves health. And our starting point would be to see that health is complexity matching. So matching of interrelated complex systems. So this is a very different way of looking at health from our traditional ways, where the focus is maintaining a steady output. Of course, again, this way of thinking has gone back thousands of years, and it has been said that there's been nothing new since the time of the ancient Greeks, or everything else is merely a footnote in history, and I do have a lot of time for that approach. Because Stoics, the ancient Greek Stoics, saw health as a state of harmony when the logos of the soul resonated with the logos of nature. And Eastern philosophies, I mean, Chinese philosophy and Chinese medicine saw it very much as the harmony of inner and outer world. So I think these ancient people had quite a few insights that we can learn quite a lot from. And there are a number of perspectives in the literature. I think there's been a lot of work looking at chaos theory and how chaos underpins healthy interacting systems. It has been said that chaos is the mother of physiology, and we can see chaos as a marker of health, and through chaos we can see matching systems using their chaotic markers and their coherent dynamics of interrelated subsystems as healthy ways of system performance. So just to give you an example of this, one of the most useful and simple areas to get hold of is really cardiac physiology, because you can measure cardiac dynamics so much easier than any other area. And we can see that there are three types of dynamic behavior. We can get simple oscillations, we can get irregular behavior, or we can get a behavior that looks irregular but in fact is chaotic, so it has an underlying pattern to it. So both these types of behavior are unhealthy. This is ventricular tachycardia, this is ventricular fibrillation, both of which are life-threatening. Chaos is a marker of health, and as we shift away from chaos, we become less healthier. Our systems become dishealthier. So let me give you a practical example of this. Let's assume that we've got 100 elderly people who have high resting pulse rate, and we know that 10% will develop heart failure within the next year. High pulse rate is a marker of impending heart failure, but we don't know who will develop heart failure. We can look at this with inferential statistics, but we don't know which individual patient will get into trouble. If we look at these people through our non-linear lens, we can see that the healthy people, this is a phase plot, we plot heart rate at any time against heart rate at any time in the future, and this time in the future can be any interval. Whichever interval we have, we'll see this picture. And what we're looking at here is, it looks very much like that chaotic attractor we saw previously. It's a chaotic attractor. and this is scale invariant. It doesn't matter where we take our interval, this pattern will be exactly the same. This shows us a healthy heart. It's demonstrating chaotic dynamics, and it's sitting on an attractor. This is a person who hasn't got demonstrating that, and this is the person that's going to get heart failure. So loss of chaotic variation is looking like an early sign for heart failure. The first thing that starts going is this chaotic or this non-linear feature, dynamic feature. So I put together some of these insights in this paper, when was it, 2005, about migraine. And I suggest that migraine may well, and there was some circumstantial evidence around this, that we should be looking at the brain as interrelating complex or non-linear networks, and dysfunctional consequences can arise when these interacting networks do not match in terms of their complexity signature. And I thought this was quite an interesting perspective, and this paper has been totally ignored, hasn't been cited once, but so that's like people, we all do work very much in our silos. So from a complexity perspective, we can say that physiological health, that chaos is a marker of physiological health, and it is the signatures of interacting subsystems that need to be coherent from a non-linear perspective that is a marker of health. And in fact, as we get older, whichever variable you look at, the chaotic signature will decrease as we get older. What about individual health? Well, the 1984 World Health Organization definition reminds us that it is the ability to flourish, and in the West we see this very much as increased materialism, an expansion of the ego, whereas from a complexity perspective we might see this more from an Eastern philosophical perspective, more of a dynamic harmony with the environment, matching our complexity with the complexity of the environment. So we take more of a relationality, a more comprehensive, holistic picture of what individual health may well be. And in fact, it was Rousseau, a French philosopher some years ago, could have reminded of that fact then, when he said that our natural state is actually being as one with nature, and it's nature's voices that instruct us to the good life. So you could argue that from a personal perspective, a complexity perspective, health is actually resonance with our natural environment. So I won't say anything more about that, but hopefully you can see that there's lots of opportunities there for applying chaos to health. And in fact, as we get older, virtually whichever variable you look at starts to deteriorate in terms of its chaotic signature, whether it be balance or dynamics or anything that varies. Our chaotic signature tends to fall off as we get older. I want to move on now to this concept of planetary health and how we can possibly match complexity to that. This is the current working definition of planetary health from the Lancet. Planetary health is the health of human civilization and the state of the natural systems on which it depends. It does seem to me that is rather a circuitous, self-referential definition, which really isn't very helpful in taking us forward. Certainly the globe does look like a complex interacting system. These are all some of the major interactions. There is a difference between what we might see as our starting point for modeling, that these interactions are quite often much longer distance than normal complex systems. But nevertheless, I think seeing planetary health, the starting point as a model of a dynamic nonlinear interaction, is a reasonable one. And as we've seen, we can demonstrate in natural systems power law scaling wherever we look. We've seen forest fires on the left there before. On the right shows canopy size against frequency of canopy size of trees, and again shows a straight line. It's number of cities against city population, power law scaling, so human systems as well. And I think this is quite interesting if we look at carbon dioxide levels over the last few thousand years. I'm not sure if anyone has analysed this, but I wouldn't be surprised if this is demonstrating power law scaling here, and then all of a sudden we go into this very much linear system as the system becomes destabilized. And I just wonder if we looked at this in a little bit more detail here, we'd start to see a fall off in self-organized criticality. So that'd be interesting to analyse that in a little bit more detail. And I think one of the things it does seem, and I don't know the literature in any depth, but it doesn't seem there is that much literature around in this area looking at planetary health from this perspective. So perhaps a better working definition would be to think about a situation of planetary health being when natural systems demonstrate self-organized criticality. And I wonder if it would be too much to also suggest that their complex dynamics are coherent, that is, in terms of their power law scaling, the power law scaling factor is similar. There doesn't seem to be, I don't know the literature in any detail, but there doesn't seem to be too much literature in this area from that perspective. So what is pushing systems away from their natural state of self-organized criticality? Well, certainly we've seen with the brain that high levels of input will cause these hallmarks of criticality to disappear as these internal dynamics are replaced by these external triggers. And I think certainly there are an increasing number of man-made inputs into natural systems. I think there are two other possible factors. One is there is an increasing amount of long-range rapid interaction. Complex systems tend to emerge from interaction at a local level, and there's more and more long-distance interaction occurring. And perhaps finally, a lot of what we do is very much dictated by so-called artificial intelligence systems these days. And again, I don't know much about them, but I suspect they're taking us away from internal complex dynamics. So those may be some of the reasons why we're shifting away from this state of coherence with nature. I'm going to move on now to some more controversial stuff, which I think is quite interesting. The start of life, applying complexity to the origins of life. So this is the evolution of man. So we've been evolving quite rapidly, but the curve does, in terms of complexity, this is the number of cell types as a function of evolutionary time. It does seem like this complexity of cell types is leveling off. And I want to go back to this diagram of entropy and complexity to just think a little bit about where complexity comes from. And I'm going to pick this up in a little bit more detail in the appendix. So I think it's an interesting concept. So we've seen with dissipative structures that as entropy increases, and this is the entropy of the universe. So we started with the Big Bang here, and entropy continues to increase. And we find ourselves probably at the top of the curve here. So as entropy increases, the complexity of systems can increase as well to a maximum, and as entropy continues to increase, and ultimately the universe becomes one large void where energy is uniquely and uniformly distributed. It's basically the end of the universe. That is, of course, until unless the universe starts contracting again, and we can come all the way back down again and pick ourselves up again here. Inevitably, complexity is on the way down. So if global warming doesn't finish us off, or nuclear war, or when we collide with our nearest galaxy, Andromeda, as it's said to happen, whatever happens, entropy is going to get us in the end. So a bit of a depressing thought. So entropy pushes up complexity. So we can map this onto this nonlinear simulations and see how simple interaction at a local level can give rise to very complex patterns. And we can see how this happens by these simple computer simulations. We can apply that to autopoietic systems. We know that bounded systems, if you look at lipids, they have a water-loving head and a water-hating tail, and they can align themselves up in these membranes, and under surface tension action, minimize surface tension, they can form membranes, spherical membranes, and you can see this is probably how life started. So we get a bounded system, which then generates a network of processes as they entrap molecules within them. and these processes form new components, which again changes the boundaries, which changes the network of processes as they interact with other systems, and so we go on. So we can see how life may have emerged from the autopoietic application of molecules underpinning self-organization at a stage where they take in energy, and this leads to systems that operate away from thermodynamic equilibrium, which drives them towards patterns of organization. I think that's quite interesting, and who knows how life has evolved. We might all be, I think it's probably equally probable that we're parts of a PlayStation game on the planet Zog, but it's certainly a useful model, which can be a useful starting point for us. So what about applying complexity thinking to language? I think this is a really interesting area. So, our first step in the world is to take in this data and codify it. We take in our sensory data and codify it in terms of language as our starting point. And there's two approaches to language. Chomsky sees language as actually being hardwired into our brains, whereas I want to follow Saussure, which takes a constructionist approach and suggests that language acquires meaning. We acquire it, and language acquires meaning from difference, going back to this basic fundamental principle of the brain as a difference engine. Language acquires meaning from difference and relationships. And it has been suggested that meaning emerges from the relationships between the structural components of the system itself. So words come together, they self-organize, and what emerges is new meanings, which then track back to the original words from where they came from. So there's no actual meaning to a word. It's a recursive system, and any meaning reverberates through the system and it ultimately feeds back on where it actually came from. So we can actually suggest that language is an autopoietic, self-organizing system. Our language is the bounded system which can change. It sets up these interacting words which form processes, which lead to new words, which again changes the boundary. So I think complexity theory can offer us some really interesting insights into language and how language may have formed and taken off. So if you're still with us, I'm sorry that's been rather long and prolonged, but I just want to very briefly reflect on why complexity theory hasn't possibly made as much headway as we may have anticipated. A lot of people have been not particularly pleasant about it. Called Emperor's New Clothes, misapplied metaphors, intellectual snake oil. There are a number of problems. The first problem is the success of the scientific method has created an illusion that we can actually unpick. The truth is actually out there, and all phenomena are governed by a set of explicit laws that we can actually find out. And this has been extremely successful. Whereas with complexity theory, we're asked to stand back, and it outlines the limits of predictability. So there's a shift from control and prediction of systems to a more general understanding. But alas, most people want certainty. And there are a number of problems which I've alluded to. So there's no accurate measure to quantify the complexity of a system or model it. It only offers us general outlines and suggests that systems may not be as certain as we think they are, or would like to think they are. So it limits our explicit predictions. And I think one of the other problems that I've alluded to is that academics tend to work in silos, and they get very resistant to change. So if you spent your whole career building up a portfolio that sits within a linear paradigm and something comes along to challenge that, you're very resistant to change. And it's quite a sort of threatening suggestion to say that you can't understand a complex system by modelling it, because we like to, wherever possible, reduce things to mathematical certainty, but we can only act within it and observe what happens. So it's a very qualitative approach, and I suspect that it will always be that way. Let me finish with a quote I like from Keynes, who was arguably one of the greatest economists of the last century. And he suggested that we have to invent wisdom for a new age, but in the meanwhile we must appear unorthodox, troublesome, dangerous and disobedient to those that begat us. So I think complexity may or may not be this new wisdom. It's probably early days, but certainly if it only sensitizes us to the interplay of patterns that are perpetually transforming our environment, it can give us an avenue to do things just a little better. So that's the end of my sort of formal presentation. I want to pick up on a few appendices. I want to say a little bit more about Ashby's law of requisite variety. I want to say a little bit more about entropy and complexity. And I want to say a little bit more about language. So I just want to give you a simple example of Ashby's law of requisite variety, which is, I think, very important. So let's assume that we have a system with 5 variables, and the system within which we seek to control it has only got 2. So to have an adequate control here, or for systems from a complex perspective to be adaptive and coherent, we need to have the same number of variables in both systems. So our system needs to operate on this law of requisite variety. So the variety of our stimuli, or the number of variables, must match the number of responses, or the number of variables of our controller must match the number of variables of the system we seek to control or be coherent with. So they invariably don't match. So what we've got to do is we have 2 options. We can either attenuate or filter the number of variables in one system, or we can amplify the number of variables in the other system to make sure there's matching between the 2 systems. And here's an example, simple example of this. So say I want to control the weather, the 5 variables of the weather, and I haven't got any variables at my disposal. All I can do is build a filter, so I can build a house. So whereas 5 variables were trying to match 0, I've built a house, and now I've reduced the weather to 1 variable, which is temperature. So 5 variables are now matched with 1 variable. It's still 1, 0. So I can build myself an amplifier. So I build a central heating system, and I have a regulator that switches the heating on and off to match the temperature. Now I have, by a process of filtration and amplification, a system where 1 variable matches 1 variable, and I'm happy I've got a perfectly effective and efficient control system. So that's a very simple example of Ashby's law of requisite variety. The next appendix I want to look at is just a little bit more about entropy, to give you an example of entropy and complexity, which I think is quite interesting. So we've seen that as entropy goes up, complexity increases as energy is taken into the system before decreasing again. So entropy you can look at as a degree of disorder, and the second law of thermodynamics states that the entropy of any system will inevitably increase. So the entropy of the universe continues to increase from the Big Bang. So we can look at entropy as how many ways we can arrange small scale components to give large scale properties, or alternatively how spread out is the energy in the system, as energy will always seek to obtain an even distribution across the system. So this compares with complexity, and we can look at complexity by asking ourselves, how difficult is it to describe the system? And here's a good example of increasing entropy and complexity. So we have milk and coffee, and from a macroscopic scale, these 2 systems have low entropy states, so the degree of disorder in both these states is, from a macroscopic perspective, low. So we will increase the entropy of the system by applying energy. We will start stirring it, we'll apply mechanical energy, and for a brief moment we get these patterns, these swirls occurring in the system. So the system now is moving up to here, and then as we continue to add energy to the system, the complexity decreases into a homogeneous, increasingly random system as entropy increases still further. So as we put energy into this system, there's a transient increase in complexity before it decreases again, back to a state of energy distribution or increasing entropy. So as entropy of a system increases, there is a zone where energy is taken on board, where systems can increase momentarily their complexity, although they are not at equilibrium with their surrounds. Finally, I want to speculate somewhat wildly about language, which I think is quite interesting. The whole of 21st century philosophy has basically been a concern about how language relates to the world and how language relates to the mind without any convergence whatsoever to any unifying. And let me just reshare again this slide, which I think is quite an interesting one too. The brain has three types of dynamic behavior: this low frequency regular behavior, this random behavior, and this is the one area we're interested in, is the scale-free or self-organized criticality behavior, where we can demonstrate power law scaling. And let's just recall the fact that cognitive load, and for a cognitive load I think we can fairly say language will reduce the criticality of the brain. So when we started off on our evolutionary pathway with very simple nerve nets, very simple nervous systems, we can say with a reasonable degree of certainty that these systems, the dynamics of these systems, matched the complex dynamics of their environment. So there was self-organized criticality demonstrated here, which matched the self-organized criticality of our environment. So we were in harmony with our environment, in harmony with nature. And somewhere along our evolutionary path, things must have shifted. When and how did this happen? Interesting observation that hallucinogenics shift brain dynamics towards criticality as well. I say that because one of the recurring themes from people that have taken LSD and psilocybin, other hallucinogenics, is they get an insight into the interconnectivity of the universe. It's a sort of common theme that comes through, which I think is quite interesting, as the brain moves towards this more self-organized criticality. And I think what these things do is actually switch off the, they act on a number of areas, but they largely switch off the default mode network. And I think one of the things about language and its power is its ability to respond to Ashley's law of requisite variety. So language starts as a communicative tool, simple communicative tool, but takes off very rapidly because it's able to both amplify and attenuate in systems, in matching systems. So metaphor would be an amplifier, tone, intonation would be amplifiers. Words are narrative, storytelling, even words themselves are attenuators. So language, as it evolves as a self-organized autopoietic system, is able to match complex systems very efficiently through these devices that are present within it. But things go badly wrong when this language gets appropriated or misappropriated to our tacit model or explicit models of the world, our visual networks of the world, and worse still, our more basic patterns of behavior, which we call emotions. So this then gives rise to all these things such as sense of self, ego, sense of time, sense of mortality. And language has its advantages, but possibly it's given us more problems than it's been worth, because what it does is detach us from our environment. It starts to detach us. We've seen that language reduces cognitive, increases cognitive load, which reduces self-organized criticality in the brain. So I wonder if it's language that's taken us away from this natural harmony with our environment, our harmony with nature, and has allowed us to take off to potentially future detrimental effects. This was arguably the greatest philosopher who studied the problem with language in the last century, Wittgenstein. Limits to language are the limits to my world. And he looked at language as a ladder, if you like. It's a good metaphor. So you climb up this ladder to understand the world, and you look back. You can only get so far, and you can see that you can go no further, because language has this recursive flavor to it. So when you look back and you see that the ladder itself was only a mere illusion. So Heidegger, German philosopher, suggested that man acts as though he's the master of language, whereas language actually is the master of man. And in fact, we bring forth the world, whatever's out there, in terms of language. And I'm interested in this myth of the Garden of Eden, which is a recurring myth in a number of ancient historical texts. And I do wonder that if the apple reflected the acquisition of language. So the fall of man, before the fall of man, we were in a state of harmony with nature, self-organized criticality with nature, and we developed language, and this was the start of our demise. And this is what this myth is all about. Anyway, I'm getting slightly off track here, so I'm going to stop now. But hopefully, you would have gained a little bit of an insight into how complexity may offer us some useful insights, but also its limitations.